This is section 0.2 on the binomial theorem. I've got some definitions before we get to the theorem, and then we've got a proof using the principle of induction. Let's get going. So I need to start by telling you about binomial coefficients, which are defined for natural numbers n and k with some restrictions on the values of n and k as n factorial divided by k factorial n minus k factorial. And I write these using brackets like this with n over k inside large brackets, not to be confused with fraction, not to be confused with a vector, not to be confused with a Legendre symbol. There are lots of things that people use this notation for, is my point there. It's pronounced n choose k, and sometimes people use a different notation for it. So some people don't like that notation and they write n capital C k with the k down here as a subscript and the n up there as a superscript, which makes me feel slightly uncomfortable to have the superscript on the left, but that's what people write. Either way you write it, there's a convention that if k and n don't fit those inequalities, that this is 0 by convention or maybe by definition, that you have 0 for other pairs of k and n. The formula comes from the idea about choosing things. It's the number of ways to choose k things from a collection of n things. And the formula comes from an idea about overcounting. If you line up the n things and say that you will take the first k of them, then there are many ways to line them up, n factorial ways to line them up. But if you don't care about the order of your k things, or the order of the n minus k things that you're not picking, really unlikely you care about the order of the other n minus k things, well, you can divide to allow for that overcounting for the permutations of the things you're picking and the things you're not picking. And there's a formula there. I'm not going to talk about combinatorics and choosing for the rest of this video, but it is an important application of this mathematics that you can do. You can use these things for problems involving choosing. My aim is to prove the binomial theorem. First, here's a picture of the numbers laid out in a triangle. Lots of different cultures and civilizations have different names for this triangle. I am going to call it Pascal's triangle, even though Pascal was by no means the first person to arrange those numbers we just saw in the shape of a triangle. The property that I want to talk about is that each number is the sum of the ones above it. When you lay them out like this, and laying them out in a triangle is very pretty. The algebra is less pretty. Let's look at a statement here. So here's a lemma. Lemma is a small result that you get before you prove a theorem. So lemma 0.16, which I've tagged as Pascal's triangle, also Yankee's triangle or Tartaglia's triangle. Other names for the triangle are available. Let n and k be natural numbers, with k between 1 and n inclusive. Then the thing you can do is you can do n choose k minus 1 plus n choose k, and you'll get n plus 1 choose k. In words, if you're thinking about choosing, I know I said I wouldn't, but here we are. If you have a collection of n plus 1 things and you're choosing k, then you can either choose from among the first n, or you can take this you can take this n plus 1 thing, this new thing, and then you only have to choose k minus 1 of the original n. So there's two ways to get those choices. Algebraically, you can prove this just using the definition. It's not very fun, but you just need to put those two fractions, because they really are fractions, over a common denominator. So they both involve n factorial, they have different denominators. Using the definition of factorial, you can work your way through this. So for example, in this first one, I need to multiply top and bottom by k to get k factorial down here. And in the second one, I need to multiply top and bottom by n minus k plus 1, the next number. And then when all the dust settles, things simplify nicely. I get actually the denominator I always wanted, which was to have 1 more on n. And upstairs, I get precisely n plus 1 factorial, which is just what I wanted. The algebra here completely disguises any idea about choosing or any idea that this is a combinatorics problem, but there's the algebra to prove a lemma. Now, what I'd like to do with this is some induction, because this lets us get from binomial coefficients involving n to binomial coefficients involving n plus 1. So we're going to use this as the central idea of the inductive step of a proof that goes from n to n plus 1. Here is the claim. It's a theorem, the binomial theorem. Let x and y be real, all complex numbers. We haven't defined any multiplication or addition on complex numbers, but this still holds. In fact, I haven't defined really enough of the powers and commutative multiplication things for real numbers, but maybe you can prove some of those on the example sheet. Let n be any natural number. Then the result is that x plus y to the power of n is, and then there's a big sum on the right hand side, lots of terms added together. Remember the sum starts at 0, ends at n, includes both of those numbers. It's a whole load of powers of x and y with different powers, x to the k, y to the n minus k, and the coefficient on that term is the binomial coefficient, n choose k. It all fits together like that. We're going to prove this by induction, and we have to induct on a natural number. So we're going to choose n to be the thing that we induct in, not x or y. That would be a bit much. Okay, so here's the proof. We've got to check for that it holds for n equals 0, but that's fine because the thing on the left is x plus y to the n. That's just 1. And on the right, we've got a sum that only includes 0. So we only have to think about that term. And even better, the binomial coefficient on that side is just 1. So now assume the expression holds for n, and we're going to prove that it holds for n plus 1. So we're talking about x plus y to the n plus 1. As always with a proof by induction, you need some idea about how p n plus 1 relates to the previous case, or maybe all of the previous cases. And here our idea is quite straightforward. Our idea is that the power of n plus 1 means the power of n multiplied by yet another x plus y. So this relationship between n plus 1 and n is crucial for a proof by induction to get from large number to previous case or cases. Okay, our mission is to multiply this by x plus y. And we know something about x plus y to the n. We know that it is this enormous sum of terms. So my plan is to multiply that out by x and by y. I'm going to do those things separately because the powers are quite nice, right? The powers in there are grouped together. So I'd like to multiply by x. I can see how to do that. Just add 1 to the exponent. And I'd like to multiply by y by adding 1 to the exponent of y. And I'll add those quantities together. So it's been quite strategic with how I multiply out by x plus y. I could expand the sum and write out lots of terms, but I'd like to multiply the whole thing by x. That's not too bad. Multiply the whole thing by y. That's not too bad, and add them. That gives me these two terms where you see I've incremented the exponent here and I've incremented the exponent here. Okay, that's just what it means to multiply something by x plus y, is you will get all of these terms. And then so that I can do the next thing that I want to do using the lemma, I'm going to pull out the very first term of the first sum, sorry, the last term of the first sum, and the first term from the second sum. So I've pulled out this x to the power of n plus 1 and this y to the power of n plus 1. That's technically because my lemma only holds for certain values. And I need to exclude these terms from the argument that's about to follow. If I'm honest, you do something in general and then you check whether it holds at the edges, and if you need to treat the edges separately, then you come back and you pull them out of the sums like this earlier on. Okay, here's the idea. These sums are pretty similar. They both involve powers of x plus y, and in both cases we sum over lots of different exponents, but it's always the case that the exponents add up to n plus 1. In both sums, the exponents always add up to n plus 1. And that means that we're going through the same combinations of powers of x and y as we go through each of those sums. They both include, if n plus 1 is 30 or something, they both include a term that has x to the 3, y to the 27 in there. The difference is that they're sort of out by 1, that this one is talking about x to the k plus 1, and that one's talking about x to the k. And this one's talking about y to the n minus k, and that one's talking about y to the n plus 1 minus k. So they're sort of out by 1. We can fix that by relabeling one of them. I'm going to relabel that first sum. So I'm just going to take this first sum. Notice also the limits on the sums are different. This one goes from 0 to n minus 1, that one goes from 1 to n. So I'm going to take this first sum, and I'm going to try and make it look more like the second sum. It's not equal to the second sum, but I'm going to try and move it towards a more similar notation so that I can see what's going on. Spot the difference. The limits are different, the exponents are different, and at the moment the binomial coefficients are the same. I'm willing to make that change because I can work with binomial coefficients. Okay, so on the next slide, I've got that first sum, but I've rewritten it twice. What I'm doing here is making a change of indexing variable to get from the first line to the second line, and then I'm relabeling to get from the second line to the third line. And this has an overall effect that I'd like to describe. I would like to do this in slow motion. Here we go. So to start off with, I'm relabeling with k equal to L minus 1. The reason I'm doing this is so that I can have a sum that starts at 1 and ends at n. My idea is that the index value should be 1 larger. And of course I can't just sum with different values being plugged into the function, so I have to make that change everywhere. So if I put k as L minus 1 here, and also here and here, then I get minus is plus, so I get this plus 1 in there. I get different exponents. I get L minus 1 in L minus 1 in the binomial coefficients. That's moved me in the direction I want to go because things are starting to match up with that other sum that was about the sum from 1 to n, and where the exponents were subtly different, out by 1. So to get from the first line to the second line, I'm making the change that k should be replaced with L minus 1 to give me the fact that these two sums are the same. Okay, so now I've got a sum from 1 to n, and the idea that I'd like to do here is that L is a sort of dummy variable. It doesn't matter. This isn't a function of L. L isn't some parameter that we're given by the question. It's not secretly equal to some number like 3 or something. It's just something that we're using to indicate where the sum is happening. So it's perfectly fine to relabel this sum using any letter that we like. Not X or Y or N, I suppose, they've got special meanings in this question, but to just relabel to say like this, to just relabel should give us this expression with K's in instead. I could use any letter, like M or Q or whatever I want. I'm highlighting this in slow motion because it probably looks like I've committed some cardinal sin by having, on the one hand, a swap where k is L minus 1, and on the other hand, a swap where k is L. Of course, these can't simultaneously be true. And this is okay because we're just relabeling dummy variables. I'm not making a claim about any actual parameters in the question. K and L aren't in the question. I'm just making a change of which letters I use through the sums. So you're right that the combination of these equations together has no solution. There are no values of K and L for which you start and you end with pointing at the same thing. And that's because I've done the shift. I've shifted everything along. No term stays still in that shift. So there's no number that tracks all the way through. The values of k at the bottom are, in a way, different from the values of k at the top. They go over a different range, for example. But there was never any such thing as k in the question anyway. So if you like, what I'm doing here is changing my mind about what k means for this sum. Okay. So you need to be happy with both of these ideas in order to work with more complicated sums and, in some sense, processes later on in a mathematics degree. Both the idea that you can do a sort of substitution, a change of variables. That first step might be familiar from some calculus course that you've done where you make a substitution, but also the idea that you can relabel, and that these are both okay, even if you end up using the same dummy variable as you were using before in a different context. Okay. All of that is so that I can get these limits on my sum to make it look like the other sum. Let's plug it in and see what's happened. So I've now got 1 to n, and my binomial coefficient has changed, but my exponents now brilliantly match up with the ones in the other sum. So now I can bring these terms together. Good thing I moved out the other terms because they're slightly different, but I can bring these terms together. The sums just match up. We're summing from 1 to n in both cases. We have the same powers of x and y. It's beautiful. So we have this sum in the middle. I get to use the lemma to say that we can add those coefficients together, put the first and last terms back in, and we get exactly what we want. The proof just falls over from there. So putting all of this together is really just an exercise in relabeling and changing the index variables in one of those sums, together with, of course, the definition of power of n plus 1 and the inductive hypothesis and using this lemma about binomial coefficients. But I think the real idea, and the thing I really want you to take away from this, is this idea that you can work with sums to change the variable that you're using. Okay, that's the proof of the binomial theorem using induction, and that's the end of section 0. So I'll see you in the next video for a new section where we look at sets. See you there.